So I must admit, it's a very intimidating audience to be presenting to. I'm very humbled by the caliber of talks that have been presented. Today, I'm coming to you unashamedly as a hardcore software developer, programmer, and I'd like to present something that's been very close to my heart for quite a while now. This is part of my PhD research. It is very low level compared to the talks I've been hearing about, but it's something that I hope you might find interesting, because I feel that there's great applications that are relevant for the topics we've been talking about. So there's quite a lot to cover. I'm going to dive straight into it. I'd like to go back quite a long way, all the way back to the background of computer science. The inventor of the Pascal programming language, Mr. Wirth, he wrote this incredible book where algorithms plus data structures equal programs. And Pascal is actually very, very close to my heart, because that's the language that I started coding in when I was a child. And I've even got my book still that details how to get started with Pascal. And I'm happy to say that the book has aged a lot better than I have, actually. So it's interesting how certain good ideas stand the test of time. So what I'd like to just begin with is a refresher of some of the fundamental data structures that have emerged from computer science. And the relevance to our topics are that these are the foundationary concepts that we've all been building on top of, especially in the data science world. So the first data structure is quite simply the list. And it's fairly simple. It just holds a bunch of items. The next data structure would be a map, where we extend this idea and we associate a key with some value. And this allows us to perform lookups and map items of data together. The next data structure would be the tree. This is very powerful. We see it a lot in our file systems, on our computers. It's a very effective structure to encode hierarchies of information, to encode decision trees. And it's made up of a root node. Each node in that tree will have relationships to its parent node or its child node. And the leaf nodes are right at the end of that tree. The fourth fundamental data structure is the graph. And this is characterized by vertices and edges that connect together. These are the four fundamental data structures that we've really been using for many, many years in computer programming and data science. The interesting question for me has been, well, what is the next data structure to exist? And the rest of my talk really unpacks this idea. And I'd like to propose that the repo is that next data structure. I'd like to make the connection to why it's so valuable as a data structure, especially for the area of AI and explainability that this conference relates to. So what might this data structure look like? Well, if we think of it as a foundation on which you could have a content area. Now, what does that mean? It means you can just put information into it, and that might look like a file system. So you can think of it like files that you might have on your computer, but I'd like you to imagine that file system in memory. It's a virtual file system, and it allows content to have a certain path so that it can be accessed by a path that you can imagine like the paths on your computer. What we then want to do is to be able to commit that content area, make a snapshot of it. And then what we do is we can start modifying the content. So maybe you can change certain values, maybe you can add more content, but you could also leave content unmodified. And then you can snapshot that again. You can keep going and keep building up history with these commits. So at every step of the process, you can modify the appropriate data as necessary. And we keep track of that history in the commits, in the graph of commits. So this is what it may look like. I'd like to introduce this as that next data structure and then explore how it can be quite useful in various scenarios that we encounter. There's something quite interesting about the repo, which is very powerful in terms of a lot of the scenarios we experience in AI. We can create a branch of the history to say that we want to track some of the changes with a label. And then you can have multiple branches at once where you are manipulating different aspects of that content. And you can keep track of all of that information in a neat data structure. So my proposal is that the repo be looked at as the next data structure in that traditional progression. And this is what it may look like. Now that picture gets a little bit messy to keep drawing. So I'm just going to go back down to that simpler one with the 3 commits. The next idea for me is to explore the nano scale of modeling. I want to just spend a little bit of time on this because I found in my research that focusing on the nano scale and coupling it to the version control that the repo provides is actually the trick that we need to embrace. So if I just draw one concept like this, the shape of the colored boxes might indicate different types of concepts. This would be 2 concepts, and then this would be many concepts. So if you are comfortable that we may represent one or multiple concepts in a data structure, and then there's a spectrum in between those points, we can start to understand that the types of information that we want to put in these structures may vary. So the nano scale of modeling is really about taking that repo and applying it to only one concept. I'd like to contrast what database modeling might look like. And here you would see that in one database, you would have multiple rows in a table. Normally we would put all of the same concepts together in one table. I'm just drawing them in different colors to distinguish that a bit more easily. But this is how I would imagine a database looks like. It's able to store multiple concepts that we're modeling, usually in separate tables. But its job is to keep those, those rows or those instances of those concepts together. If we contrast that to the way that I'd imagine the Nano repo store, we do something completely different. We basically replicate those repository structures multiple times, once for each instance of the concept. That's quite different to how you imagine or how the database is actually implemented. Another thing to contrast is, well, hang on, some of you who might be working with software development will say, wait a minute, this sounds just like Git. And yes, you'd be absolutely correct. It does sound like Git. I just want to highlight that the way that Git currently gets used for software development, for version controlling your software, your source code, for me belongs on the far end of the spectrum. So I imagine it as being something like this, where you'd add a piece of content, you'd commit that, you'd add more instances of that concept, maybe different types of concepts, and commit those. And then you'd keep building that commit history. So for me, that is what I would imagine the different data structures would look like. And that contrast is quite important to understand. So I would like to just spend a bit of time reflecting on the structure of Git. A lot of software developers and data scientists will be using that to version control and collaborate with people around the world. And it's Git in particular was used to manage the development of the Linux kernel. But it's basically taken over the world as the de facto or the most popular technique for version controlling software. So I'd like to just spend a bit of time to reflect back on the original data structures that we looked at. And I don't think many people ever bother to look under the covers to see how Git is implemented. But for me, it's been quite fascinating to take a look and see how each of the fundamental data structures feature quite prominently in different parts of that Git repository. So those that are using Git, if you ever want to venture into that .git folder and poke around a bit, you might find this picture quite valuable to just try to make a bit of sense of it. So this is what, if I made an attempt at drawing a Git repository, this is what I would imagine it looks like. And you can very clearly see the different types of fundamental data structures that exist there. The reason I bring this up is because what I'm exploring with my research is the idea of version control, but contrasting it, pulling it out from being tied to the disk and file storage, and exploring what would happen if we implemented it in memory. And that's what the foundation of my research really is that if you have in-memory version control in a manner that I've shown you with those data structures, and then you couple it with nanoscale modeling, it's really those two things that give us the nano version control. And this is a similar idea to Wirth's original algorithms plus data structures equals. So it's very interesting for me how to sort of couple those two ideas together. We've got an implementation of nano version control working. It's actually through its second major overhaul. And if you're interested in checking it out, please, I urge you, go try it out. This is a glimpse of what it may look like. It's in Java, but anyone who's familiar with using Git on the command line or using tools for Git will immediately start recognizing how you can just start committing content, checking it out or creating branches, and then comparing different commits to see the differences. So that's the beauty of this idea for me, is that anyone who is currently familiar with Git can automatically transfer all of that knowledge that they have from the disk-based system for their source control to this data structure that becomes quite valuable for various reasons. Something else that we've got early results around is just the sheer performance of being able to work with this data structure in memory is quite exciting for me. And it shows quite a lot of promise. So with a simple performance test of a reasonable amount of data, if we have three operations of committing, branching, and then merging those branches, and we do that 1 million times on some randomized data, it takes 3.7 seconds on my laptop. These are results from last night, which gives us an incredible 267,000 repos being processed per second. Now, the truth is, what you might be impressed by with those stats is really the implementation of hash maps and efficient data structures that the Java team have developed, or it's really a consequence of the performance of the other data structures. But being put together in this repository, in this repo configuration, means that we can start building higher level history-based operations using this data structure. And anyone who's tried to commit files or content to Git will realize that you get nowhere close to 1 million repos or 1 million commits per second using the normal disk-based approach. So for me, it's quite exciting to see the massive performance boost, which for me may be several orders of magnitude faster, by simply lifting the capability to have history out of your storage layers, out of your databases, into a data structure in memory. And then the role of the storage layers ultimately becomes to store the data, not to give you the history. And that's really quite an exciting prospect for me. The connection to the content for the conference is that I've noticed that there's a very severe imbalance at the moment where Git and our version control, as we know it from the Git world, is predominantly used for version controlling source code and the algorithms. And there's an extremely mature set of tools and online hosted repository services like GitHub and Bitbucket, which are designed for the version control of the software. So the auditability and the maturity of being able to track changes in the software, to understand how the software ultimately ties back to some sort of business driver or some objective, and being able to explain what has changed in the software, in the algorithms, that is extremely mature today. And it's incredible to see how in a very short period of time, the tooling, the support, the cloud infrastructure around these things, the collaboration between software developers is absolutely at a futuristic sort of level that I would never have imagined when I was reading these books all those years ago. What's also very clear to me is that there's a huge gap in terms of the data structures that exist that allow us to get similar type of fairness, transparency, and explainability for the algorithms that we're running and the data structures that we're creating with those algorithms. And that's why I would like to propose the Nano version control repo as a fundamental data structure that can help us equalizing that imbalance. I've been fortunate enough to work on several AI applications in the mining industry, and now more recently in the fintech industry, the financial industry. And for a long time, I've had the sense that, there's something missing. When you're coding these things, there's certain problems that you keep running into. A lot of them being hard problems around the transparency and explainability of changes to data, or how decisions get made throughout algorithms or AI approaches. And I've been missing, there is something missing for me. There's been this data structure that doesn't exist, but somehow seems familiar. And that's the connection that I'm making, is that everything we've been learning from the Git world, if we just had that as an in-memory data structure and we started learning and teaching students how to think in terms of histories and branches, then I think a lot of these fundamentally difficult problems that some of these great speakers in this conference have been mentioning, I think could be substantially simpler to explore, to research, to deliver on. So my sincere hope is that this could be the beginning of exploring or equalizing that imbalance and understanding where could this data structure start assist AI researchers or data scientists or even software developers to stop focusing on history type problems or explainability and traceability problems, because the data structure is designed for those, and we can start thinking and executing at higher levels. There are a couple of areas that we already have some interesting results around, and these are the specific areas that I'm continuing to explore for my PhD. I mentioned the applicability to computer science as a data structure. The significance of this could be that there's possibly a new chapter in the computer science textbooks where students are learning the repository and this data structure, which is designed for tracking history and changes as a fundamental data structure. The implication of this for storage and databases is quite interesting. So a lot of databases currently do provide you the ability to store different versions of your content. And this application is interesting because maybe it provides an intuitive, familiar API, an interface for querying that history, as opposed to forcing that concept into historically inappropriate structures like SQL, for example. There is research being done in how do you have history in SQL and those sorts of languages. But I'm providing an alternative, which is why not use the model that you're currently familiar with. In terms of the implications of the data modeling spectrum, I'm finding in the financial domain, by embracing this idea of modeling an entire client at the nano scale, so that all records for that client, be it demographic data, financial data, transaction data, all of that information is stored in one repository, has very interesting implications for things like GDPR, where you are forced to allow a client to say, please remove me from your databases completely. And in all of these monolithic, large-scale database structures, especially around the history, that is almost impossible to achieve. It's very difficult at best and usually impossible in the normal case. So this provides a different approach where if a client wants to be forgotten, or they want to exercise that right to be forgotten, it's as simple as deleting that repository which contains all of the history, which gives us a new angle, a new data structure that is very appropriate for a typically extremely painful thing to achieve in the real world. I'm exploring aspects of distributed and cloud computing. So if we remove the capability to have history from the database, we're finding that in a lot of data flow pipelines where you want in parallelism in that pipeline, the Nano repo is very effective because you no longer need that central dependency on your database to provide history, especially coupled with the Nano version, the Nano scale of modeling. One concept's entire history can be passed down the data flow pipeline as a value. So you can commit to that history. You can create branches, which you could think of as alternate realities on that data structure. You could gather it up at the end of the pipeline and then decide what you want to store, what you want to persist to permanent storage. So it opens up very interesting possibilities for algorithms that are traditionally coupled to a central database for that history. Around data quality, if anyone who speaks French in the audience would like to maybe unmute and say the word provenance, I think the French accent really does it justice. So, if anyone is there, just shout it out quickly. I think it just sounds so beautiful, provenance. And that's really relating to the data lineage. Are there any French-speaking guests in the audience? I always love to hear them say the word. Any volunteers?
I can't. Yeah, I actually can't see. I can't see anybody that pops out to me.
Out of luck today. But I think the idea of explaining where, the lineage of where the data comes from or what decisions have been made, I think is especially useful for this talk. I'll show in a few slides an example of that. This has applications in event streaming, some new technologies or fairly new technologies like Kafka and other streaming platforms highlight the ability for us to invert the database. And they highlight the duality of the table structure in a database and the event log. What I'm proposing with the repo is that there's a third representation where you aren't losing the history. So the table, the tabular structure in a database is really just the final snapshot, the final state of all the events that have happened. So for me, the Nano repo becomes a representation that doesn't lose that history from the event stream, which is quite exciting. And then I'll also show 2 slides on the AI and the agent-based simulation. So just being able to arbitrate or implement agent-based systems. So as an example with the provenance, there is a standard that has been defined, a W3 standard, around the concepts that are important for provenance, which is to track how information has changed, why it's changed, who's changed it. And this is very well established. And from my perspective, practically, it's very well thought through. They've captured the really important and also difficult aspects of tracking provenance and given them standard names, standardized the terminology. So this is what it may look like in a repo, where the file-based, the tree-like structure of the content means that you have effectively infinite detail, sub-detail, sub-tree structures that you can start augmenting your content with. So in this example, if the green blocks on the right represent the entity information, you might have the agent and the activity information augmenting that content inside the repo, and that can be version controlled. With the agent arbitration, problem that I've never really been satisfied with the current agent simulation frameworks is if one agent wants to make a change to the environment, let's say in this example, they want to modify that gray block at the end. If the green agent wants to make it green and the red agent wants to make it red, who should win? So there's a conflict when you want to merge their 2 approaches, their 2 algorithms. So with the Nano version control way of thinking, I see this quite simply as well. Instead of having a heuristic that will determine or some sort of score approach that will arbitrate that dilemma, my frustration is that tends to presuppose a solution in my experience. This approach says, let's create a copy of the universe where the green agent won, and we call that a branch. And then another branch in that repo where the red agent won. And then your algorithms can basically run in parallel on those branches. And at first, I must admit, I thought that the solutions, and these branches represent multiple solutions to the problem. At first, I thought that these would explode very quickly. But for the simulations and the applications we've been running, I'm pleasantly surprised that in the majority of cases, the agents agree, or they're not modifying content that causes a conflict. So it's very interesting because you can then find these alternate solutions to that problem, and it fits very naturally into the repo history and the branching structure. So that's really it. I think if you've followed along there, it's been an extremely low-level dive into the fundamental data structures of computer science. My sincere hope is that this presentation or this way of visually understanding the data structure hopefully sparks some interest so that the other researchers that are thinking at the very high levels maybe start reimagining some of the problems or algorithms with this data structure. Thank you.